Welcome to Standard 12th Physics Syllabus. We'll be starting with the first chapter from your book named Rotational Dynamics. Rotational Dynamics is divided into two subparts. It starts with circular motion and the remaining part deals with rotational motion. One thing to be remembered, that if you want to understand rotational motion, it is necessary to understand what is called as a circular motion. But to understand circular motion, it's not necessary that you should know what is rotational motion. Let us define what is called as circular motion. It's the motion of a particle along the circumference of a circle. To understand this concept, let us take few examples. We are aware of the motion of the tip of the hands of the clock. We know that the earth revolves around the sun. The motion is almost circular. When we are driving a bike or a bicycle on a circular track, the motion is a circular motion. The motion of an electron around the nucleus is also a circular motion. Now we will study the kinematics of circular motion. When we talk about kinematics, one thing that has to be remembered, that we are not going to take into consideration the causes of circular motion, nor we are going to take into consideration the properties of the moving body like the mass of the body. So let us learn the first kinematic, angular displacement denoted by theta. Let us define angular displacement. Angular displacement is defined as the angle traced by a radius vector in a given time at the center of the circle is called the angular displacement. Now the question here arises, what is a radius vector? Let us concentrate on figure 1. If I take into consideration the radius OP as a radius vector OP, then I can define radius vector as a vector drawn from the center of the circle to the position of a particle on the circumference of the circle. Let us learn how to write down the angular displacement mathematically. Once again, concentrate on figure 1. If you consider the particle at point P at time t equal to 0, and the particle starts moving in anti-clockwise sense and reach at point P1 after time t. The angular displacement in this case will be theta, and the particle has moved from position P to point P1, that is the arc of the circle PP1, which is denoted by S. So angular displacement is defined as length of arc divided by the radius of the circle. This has been defined from a very simple bookish definition, that angle is arc length upon radius. The SI unit of angular displacement is radian, and if we consider the angular displacement as a vector, then the direction of angular displacement is given by right hand thumb rule. Remember, angular displacement is not a true vector, it's a pseudo vector, and it acts as a vector when we talk about the instantaneous angular displacement, because the instantaneous angular displacement obeys the vector algebra, that is the commutative and the associative properties of vector algebra, and the direction of the infinitesimal angular displacement is given by the right hand thumb rule, which states that if you imagine the axis of rotation to be held in right hand with the fingers curled around it and thumb outstretched, if the fingers give the direction of motion of a particle performing circular motion, then the direction of your outstretched thumb gives the direction of angular displacement vector. Mathematically, I can write down the same as delta S is equal to delta theta cross with R. If you observe the figure 2, you will find the vector delta theta cross with R is in one plane and delta S is perpendicular to the plane containing delta theta and R. The next physical quantity in circular motion is angular velocity denoted by omega. Angular velocity omega is defined as the time rate of change of limiting angular displacement. In more simple language, it can be defined as a ratio of angular displacement to time. The instantaneous angular velocity omega can be defined by taking the limiting value of time towards 0. So if I write omega as limit delta t tending towards 0, delta theta upon delta t at this particular limiting value, I define instantaneous angular velocity as d theta upon dt. The SI unit of angular velocity is radian per second. It's a vector quantity, same as angular displacement, but not a true vector. Let us learn what is the correlation between a period and angular velocity. A periodic time in circular motion is defined as a time taken for a particle to complete one circle. So, for one complete circle, the angular displacement will be of 2 pi radians. And so, I can define t equals 2 pi by omega. Similarly, I can define the relation between angular velocity and frequency. Angular velocity is equal to 2 pi n. Frequency n is equal to 1 upon t. The next physical quantity is angular acceleration denoted by alpha, and it is defined as the ratio of angular velocity by time. So alpha is equal to d omega by dt. The SI unit of angular acceleration is radian per square second. One thing to be noted that in uniform circular motion, angular acceleration is always 0. The adjacent block shows the analogy between the linear motion and circular motion. The simplest way of writing this equation is just to replace linear displacement by angular displacement, linear velocity by angular velocity, and linear acceleration by angular acceleration. Let us see how to represent this kinematical quantities in a vector form. We are already aware of how to represent angular displacement using a right hand thumb rule. The direction of angular displacement is given by the outstretched thumb, and the curled fingers gives the sense of rotation of the particle. And in terms of vector form, I can write down delta S is equal to delta theta cross with R, as delta S is perpendicular to the plane containing delta theta and R. The direction of angular velocity is same as that of angular displacement. The direction of angular acceleration will be same as the direction of angular velocity if the angular velocity is increasing with time. On the other hand, if the angular velocity decreases with time, then the direction of angular acceleration is opposite to the direction of angular velocity. Let us see what is the relation between linear and angular velocity. The instantaneous linear velocity v is equal to limit as delta t tends to 0, delta s upon delta t, and at this limiting value, we get the instantaneous linear velocity as ds upon dt. Substituting the relation between linear displacement and angular displacement as s equal to r theta, we get v is equal to r omega. Let us see what is the relation between linear acceleration and angular acceleration. The instantaneous linear acceleration A is equal to limit as delta t tends to 0 delta v upon delta t, which is equal to dv upon dt. Substituting the relation between linear and angular velocity as v equals r omega, we can write A equals r d omega by dt. Therefore, A is equal to r alpha. Let us define uniform circular motion. It is a motion of a particle along the circumference of a circle with a constant linear or angular speed. If we consider the equation v is equal to r omega, if the angular speed omega remains constant, then v has to remain constant. The characteristic of the uniform circular motion are that it is an accelerated motion. Why it is called as an accelerated motion? Observe the figure carefully. When the particle is moving in a circular path and it's moving with a constant angular speed omega, that means its linear speed is also constant, but the direction of the linear velocity is changing from point to point. According to the definition of vector, if the magnitude remains constant, direction changes, or direction remains constant, magnitude changes, or both changes, the motion becomes an accelerated motion. The second important characteristic that it is periodic in nature. Remember, uniform circular motion is periodic in nature. That doesn't mean all motion which are periodic obeys the properties of uniform circular motion. Let us define now centripetal acceleration. We know that when the particle is performing a uniform circular motion, the direction of linear velocity changes from point to point, and this change in the direction of linear velocity gives rise to centripetal acceleration. The meaning of centripetal, centri means center and petal means looking towards. The acceleration which is directed toward the center of the circle is known as centripetal acceleration. It can also be observed as a rate of change in velocity of an object that is associated with the change in the direction of the velocity. The centripetal acceleration is always perpendicular to the direction of linear velocity, and it always points toward the center of the circle. So mathematically I can write down centripetal acceleration, which is also termed as radial acceleration, as v square upon r, which can also be written as minus omega square r. Here minus sign indicates that the radius vector and the centripetal acceleration are oppositely directed, or I can write down as omega v. According to Newton's second law of motion, force is equal to mass into acceleration. Similarly, I can define centripetal force, the force that is directed towards the center of the circle, as F is equal to mass times centripetal acceleration. So substituting centripetal acceleration as v square upon r, centripetal force can be written as mv square upon r, which is same as mr omega square. Centripetal force arises due to some known interaction. For example, the electron revolving around the nucleus in the circular path, the necessary centripetal force is given by the force of attraction between the nucleus and the electron. This force of attraction is electrostatic in nature, and so the electrostatic force of attraction provides the necessary centripetal force. The earth revolves around the sun, or the moon revolves around the earth because of the gravitational force. So the necessary centripetal force is given by the gravitational force of attraction. If you take a stone tied to the string and whirl it, the tension in the string provides the necessary centripetal force. Now we will study what is called as centrifugal force. When we studied centripetal force, the observer was in inertial frame of reference, taking the observation, and he has defined centripetal force. The meaning of the inertial frame of reference is the frame of reference which is at rest or moving with a constant velocity. When the observer himself is in a circular motion, or any body which is in the circular motion, always experiences a centrifugal force, because the body now is experiencing a accelerated motion, and so the accelerated frame of reference has to be taken into consideration, which is called as non-inertial frame of reference. This centrifugal force experienced by the body is always directed away from the center of the circle. This force arises because of the body's inertia, and as we have already discussed, that it appears to move away from the center of the circle. It is not a true force, it's a pseudo force. This force has to be defined by an observer to make Newton's laws of motion valid in non-inertial frame of reference. Let us distinguish centripetal force from centrifugal force. The first point under centripetal force is the force required to provide centripetal acceleration to a particle so that it moves in a circular path. The first point under centrifugal force. The centrifugal tendency of the particle in its accelerated or non-inertial frame of reference is explained by assuming a centrifugal force acting on it. This assumption has to be done to make Newton's laws of motion valid in non-inertial frame of reference. Second point under centripetal force, at every instant it is directed readily towards the center of the circular path. The second point under centrifugal force, at every instant it is directed readily away from the center of the circular path. Third point under centripetal force, it's a real force arising from gravitational or electromagnetic interaction between the matter. The third point under centrifugal force, it is a pseudo force, that is a false force, since it is the effect of the acceleration of the reference frame of the revolving particle. Fourth point you can add as an example for centripetal force, like the moon revolving around the earth. The gravitational force of attraction provides the necessary centripetal force. As an example for centrifugal force, you can give the example of the drum of a washing machine or the centrifuge machine that is used in the chemistry laboratory. Now let us see and learn what are the applications of uniform circular motion. The first application, vehicle along the horizontal circular track. Observe the figure carefully. The circular track is taken into consideration, which is a flat horizontal circular track. So, if the vehicle is steady, not moving on the track, the forces acting on the vehicle are its own weight mg acting vertically downwards and the normal reaction N, which is acting vertically upwards. If the vehicle starts moving on a circular track, to keep the vehicle moving along a circular track, it is necessary that there should be a presence of centripetal force. This force is given by mv square upon r. As the centripetal force arises due to known interaction, yet the known interaction will be the force of friction will provide the necessary centripetal force. So the force of friction is equal to mu times mg, where mu is a coefficient of friction, m is the mass of the car, and g is the acceleration due to gravity. This formula has been written from the first law of static friction, which states that the limiting force of static friction is directly proportional to the normal reaction. As the force of friction provides the necessary centripetal force, I can equate the two relations as mv square upon r is equal to mu times mg. Mass gets cancelled from both the sides. V square upon r is equal to mu times g. So V can be written as under root of mu r g. The next concept is well of death. Well of death is observed by most of us when we see circus. In the circus you might have seen that a motorcyclist runs on the inner walls of the well. The forces that are acting on this motorcyclist is its own weight mg acting vertically downwards, and this weight is balanced by a force of friction that is provided between the inner walls of the well and the wheels of the motorcycle. The wall of the well provides a necessary normal reaction force, and this normal reaction force gives rise to necessary centripetal force. Ideally, we will assume that this motorcycle is replaced by a single particle, and the forces are acting on this single particle which is running on the inner walls of the well. So the normal reaction force providing the necessary centripetal force can be written as N equals mr omega square, which is equal to mv square upon r. As the force of friction balances the weight mg, we can write down the second equation as the force of static friction equal to mass times the acceleration due to gravity. That is equal to mg, that is the weight. According to the law of static friction, we know that the force of static friction is directly proportional to the normal reaction. In this case, we will take the force of static friction less than or equal to the normal reaction, and so we can set up the equation as force of static friction less than or equal to mu s times n. Substituting the value of Fs, that is the force of friction which is balancing the weight, so mg is less than or equal to mu s times mv square upon r, as the normal reaction is equal to the centripetal force. Cancelling m on both the sides, we get g less than or equal to mu s times v square upon r. So this value of square of velocity should be equal to or greater than rg upon mu s. To have this motion possible, the minimum speed that will be attained by the motorcyclist will be equal to under root of rg upon mu s. The next application is banking of roads. Whenever we ride our bicycle or a motorcycle and whenever there is a sharp turn, we had noticed that we bend a little. The extent to which this bending takes place depends upon the speed of our vehicle. More the speed, more is the bending, and this we have noticed in the motorcycle racing also. But if you are in a car or in a heavy vehicle like a bus or a truck, physically this bending is not possible. The question here arises, why we bend? We bend to provide the necessary centripetal force. And so, for the heavy vehicles like car, bus or a truck, the engineers bank the road. The process of banking means to raise the outer edge of the road over the inner edge by a certain angle called as the angle of banking. Observe the figure in which the car is now moving on a bank road. Now let us see what are the forces right now acting on the car. The forces that are acting on the car, its own weight mg vertically downward. The normal reaction, which should be normal with the road surface, is now getting split into its components as n cos theta and n sin theta. N cos theta is the vertical component that will balance the weight of the car, and n sin theta will provide the necessary centripetal force. So we will put forth the equation as n cos theta is equal to mg and n sin theta is equal to mv square upon r. If you divide equation 2 by equation 1, n gets cancelled, sin theta by cos theta is tan theta, and on the right hand side you get v square upon rg as the mass gets cancelled. So the optimum speed with which the vehicle can be driven under the conditions of neglecting friction is v is equal to under root of rg tan theta. In the previous slide, we had learned why the roads are banked. If the vehicle, like car, truck or a bus, is moving on a bank road with a certain maximum speed, that is, if its velocity is greater than the certain optimum speed equal to under root of Rg tan theta, then the vehicle starts skidding towards the outer edge of the road. The frictional force that arises between the surface of the road and the tire acts opposite to the direction of the skidding and try to keep the car in the circular track. If you observe the figure carefully, you will find the forces that are acting on the car. The forces are its own weight mg acting vertically downward and the normal reaction, which should be normal to the road surface. This normal reaction is getting split into its vertical and horizontal components as n cos theta and n sin theta. The component n cos theta, in the previous slide we have seen it balances the weight of the vehicle, and n sin theta was providing the necessary centripetal force. In addition to these forces, now the frictional force is also arising. This frictional force also gets split into its components as a vertical downward component as f sin theta and the horizontal component as fs cos theta. So under these conditions, you can set up the equation as n cos theta is equal to mg plus fs sin theta. So mg can be written as n cos theta minus fs sin theta. The second equation can be written as the necessary centripetal forces that are generated, mv square upon r, is equal to n sin theta plus fs cos theta. So if you divide equation 2 by equation 1, we get mass of the vehicle gets cancelled. V square upon Rg is equal to n sin theta plus fs cos theta plus n cos theta minus fs sin theta. Now divide our numerator and denominator on right hand side by n cos theta and substitute Fs upon n is equal to mu s. That is, the limiting force of static friction is directly proportional to the normal reaction. That is the first law of static friction. We get V square upon Rg is equal to tan theta plus mu s divided by 1 minus mu s tan theta. So the maximum speed with which the vehicle can be driven on a bank road is equal to under root of Rg in the bracket tan theta plus mu s divided by 1 minus mu s tan theta. From the above equation, it's quite clear that the maximum speed with which the vehicle can be driven on the bank road is totally independent of the mass of the vehicle. So whether it's a truck, it's a bus, it's a car, or it's a scooter, the maximum speed limit remains same for all the vehicles according to the formula mentioned above. If the speed of the vehicle is less than the certain minimum speed equal to under root of Rg tan theta, then the vehicle starts skidding towards the inner edge of the road. In that case, the frictional force acts in the direction opposite to the direction of the skidding. So here the frictional force in the above figure, you can see that the frictional force is acting in an upward direction towards the outer edge of the road. This force of friction gets resolved into its components as f cos theta and f sin theta. The component f sin theta is along the component n cos theta, and f cos theta is acting opposite to n sin theta. So for the lower speed limits, we can set up the equations as mg is equal to fs sin theta plus n cos theta, and mv square upon r, that is the centripetal force, will be given by n sin theta minus fs cos theta. So if you divide equation 2 by equation 1, we get the minimum speed with which the vehicle can be driven on a curved road that is banked with a certain angle theta equal to under root of Rg inside the bracket tan theta minus mu s divided by 1 plus mu s tan theta. This minimum speed with which the vehicle can be driven is also independent of the mass of the vehicle. The next concept is conical pendulum. From the school books we had already learned what is called as a simple pendulum, and to certain extent we have seen that simple pendulum in our physics laboratory or the school science laboratory. A conical pendulum is a pendulum whose bob always traces a circular path once it is set into motion. So we can define a conical pendulum as a point mass, that is a bob, attached to a long inextensible string and is moved in such a manner that the bob performs a circular motion and the string traces a cone. Observe the figure carefully. You can see here the bob is performing a circular motion and the string is tracing a cone. So let us imagine that the bob is at point P. The forces acting on the bob are its own weight mg and the tension T of the string. The tension T of the string can be resolved into its components as T cos theta and T sin theta. T cos theta balances the weight of the bob and T sin theta provides the necessary centripetal force. Therefore, T cos theta is equal to mg and T sin theta is equal to mv square upon r. If you divide equation 2 by equation 1, we get V is equal to under root of Rg tan theta. But V is equal to R omega. So I can write R omega is equal to under root of Rg tan theta. Therefore, omega is equal to under root of Rg tan theta divided by R. So, doing the mathematical work, omega is equal to under root of G tan theta divided by R. Substituting the value of R from the above diagram, R is equal to L times sin theta. Substituting the value of R in the equation of omega, omega is equal to under root of G by L cos theta. Therefore, the periodic time of a conical pendulum T prime is equal to 2 pi by omega. Substitute the value of omega in the equation for the periodic time. You get T prime is equal to 2 pi under root of L cos theta upon G. Therefore, the frequency of revolution of a bob of a conical pendulum is 1 upon 2 pi under root of G by L cos theta. Next application is vehicle on convex bridge. You can see the vehicle is on the top of the convex bridge. The forces acting on the vehicle are its own weight mg acting vertically down and the normal reaction acting vertically up. So on the highest point of the convex bridge, I can write down the equation as mg minus n providing the necessary centripetal force as mv square upon r. In order to just complete the circle, the necessary condition at the highest point is the normal reaction must be equal to 0. So I can write down mg minus 0 is equal to mv square upon r. So m gets cancelled on both the sides and the maximum velocity on the highest point is equal to under root of rg. Now we will study vertical circular motion, that is a motion under the action of gravity. As the motion is against the gravity now, the particle will be moving in a vertical path. So at time t equal to 0, the particle is at point A as shown in the figure. The forces that are acting on the particle is its own weight mg that is acting vertically down, which will be balanced by the tension in the string that is acting vertically up. So let us assume that at some instant of time t, the particle is at point P and it is moving in an anti-clockwise sense in a vertical path. So at point P, we can resolve the weight of the bob or the weight of the particle into its horizontal and vertical components, As the motion is against the gravity, the weight will get resolved into its components as mg cos theta, that is the vertical component, and mg sin theta as the horizontal component. The vertical component mg cos theta balances the tension in the string. Therefore, the tension in the string varies at different angles during the motion. The necessary centripetal force is provided by T minus mg cos theta. Therefore, I can write down the equation as T minus mg cos theta providing the necessary centripetal force equal to mv square upon r. Now my aim is to find out the velocities at different points A, B, C and D. So we'll start with the highest point B. At highest point B, I can take the tension equal to T suffix B and velocity equal to V suffix B. So I can write down the equation in terms of the tension as TB at the highest point equal to mvv square upon r plus mg cosine theta. The tension at point B must be equal to or greater than 0. But if you put tension at point B equal to 0 and the angle that will be traced by the string when it is moving in a circular path is of pi radians, that is 180 degree. Cos pi will take the value as -1, and so the tension that will be observed by the string at point B as TB will be equal to mvv square upon r minus mg cos theta. As TB is equal to 0, mvv square upon r is equal to mg cos theta. M gets cancelled on both the sides and we get the tension at point B equal to under root of Rg. At the lowest point A, we can obtain the velocity by using the law of conservation of energy, which says that the kinetic energy at point A plus potential energy at point A must be equal to kinetic energy at point B plus potential energy at point B. So I can write down 1 by 2 mva square plus mgh at point A is equal to 1 by 2 mvv square plus mgh at point B. So at lowest point, h is equal to 0, and at the highest point, h is equal to 2r. So if I substitute h is equal to 0 at point A and h is equal to 2r at point B, I get half mva square is equal to half mrg plus mg times 2r. Multiply the equation on both the sides by 2, we get mva square is equal to mrg plus 4mgr. M gets cancelled on both the sides and velocity at point A is equal to under root of 5rg. Let us try to calculate the velocities at point C and D by using the law of conservation of energy. So half mva square, that is the kinetic energy at point A, plus potential energy mgh at point A must be equal to kinetic energy at point C as half mvvc square plus potential energy at point C as mgh. Substituting h is equal to 0 at the lowest point and at the point C h is equal to r, that is the highest point we can take into consideration, that is the midpoint. I can write down 5 by 2 mrg is equal to 1 by 2 mvc square plus mgr, because the velocity at point A was under root of 5rg. And so the above equation is written as 5 by 2 mrg plus half mvc square plus mgr at point C. So cancelling m on both the sides, multiplying the equation on both the sides by 2, we get Vc is equal to under root of 3rg. The magnitude of velocity at point D is same as that of point C as they lie at the same height. But the direction of velocity at point C will be opposite to that of D. Let us try to calculate the difference in the tensions between the lowest and the highest point. At the lowest point, the tension observed by the string is mva square upon r plus mg, where va is equal to under root of 5rg, and at the highest point, tension at B will be equal to mvv square upon r minus mg. So taking the difference between the tension at the lowest and the highest point, Ta minus TB is equal to MVA square upon R plus mg minus MVB square upon R plus mg. Substituting the values of velocities at the lowest and the highest points, we get the difference in the tension as TA minus TB equal to 6 times mg. Similarly, I left to the readers to calculate the difference between the tension observed at point C and point B and the difference in the tension observed at point D and point B, which must be equal to 3 times mg.